Ethers may be cleaved by treatment with strong acid, namely HBr or HI. This typically involves the use of at least 2 equivalents of HX. Sometimes that's simply expressed as using excess HX. In most instances, the reaction will yield alkyl halide products as well as water as a byproduct. The reaction begins with the protonation of the ether by HX. The oxonium ion thus formed will then undergo either Sn1 or Sn2 reaction. Secondary or tertiary carbons will proceed through an Sn1 mechanism, while primary or methyl centers will undergo Sn2 reaction. In this instance, one carbon attached to the oxonium ion is tertiary. It therefore makes a reasonable carbocation leaving group, so it dissociates from the molecule. This creates an alcohol, as well as the tertiary carbocation, which is attacked by the halide to form an alkyl halide product. The reaction is not finished, however, because the alcohol can react further. This alcohol is protonated by a second equivalent of HX. The carbon that is connected to the oxonium ion, in this case, is primary, so it will engage in Sn2 reaction. The halide attacks that center, directly displacing water, forming the second alkyl halide product of this transformation. In this specific example, an unsymmetrical ether is cleaved by treatment with excess HBr. The ether is first protonated by HBr. The oxonium ion that is formed has on one side a tertiary center, which makes a suitable carbocation. Consequently, dissociation occurs, an alcohol is formed, and the resultant tertiary carbocation is attacked by bromide. This affords one of the alkyl halide products of the reaction, but the reaction again is not done because the alcohol can engage in further reaction. The alcohol is protonated by a second equivalent of HBr. When this occurs, the carbon bearing the leaving group is primary, so it can react only through an Sn2 pathway. Bromide attacks that center, directly displacing water, and this affords the second alkyl bromide product of the reaction. In the generic mechanism, and in the preceding example, the reaction proceeded through one Sn1 and one Sn2 mechanism. However, it's certainly possible for other ethers to react through other mechanistic combinations. For example, 2 Sn2 reactions. In this specific example, a symmetrical ether is first protonated by HI. The oxonium ion is connected to 2 primary centers, and so Sn2 reaction is the only option. Iodide attacks one of those centers, displacing an alcohol. This gives us one alkyl iodide product and an alcohol that can react further. The alcohol is protonated by a second equivalent of HI, and at this point, a second Sn2 reaction occurs. Water is displaced as iodide directly approaches the electrophilic primary center. This gives us the second equivalent of the alkyl iodide product. In other words, the net result of this example has been the formation of 2 equivalents of the same alkyl iodide, as well as water as a byproduct. It's also worth noting that certain ethers are only capable of a single substitution. Carbons that are sp2 hybridized, like this center in the substrate, will not participate in Sn1 or Sn2 reaction. So in this specific example, the ether is first protonated by HI, and only one carbon attached to the oxonium ion is reactive. This center is a primary center, and so iodide attacks in Sn2 fashion, displacing phenol as the leaving group. This yields ethyl iodide as well as phenol, and phenol will react no further because the carbon bearing the hydroxyl group is sp2 hybridized and cannot engage in Sn1 or Sn2 reaction. So in this instance, these are the final reaction products. In summary, ethers are cleaved by treatment with excess strong acid, either HBr or HI. The reaction proceeds through Sn1 and or Sn2 pathways. The mechanism, of course, depends upon the substitution of the electrophilic carbon atoms. And all of the rules of Sn1 and Sn2 mechanisms apply. The final products are usually alkyl halides, unless one of the carbons of the ether is part of an aromatic ring, which would preclude reaction at that center. The preceding has been an excerpt from Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback format from Amazon, or in paperback at a discounted price from Lulu.